We're asked to take a cube root of the expression 108x to the 9th y to the 5th. The 3 in the crevice of the root means that this is going to be a cube root instead of a square root. And I'm going to make a tree for the expression. And I want to see what perfect cubes may be inside this 108x to the 9th y to the 5th. Okay, so here we're looking for perfect cubes. I'll break the thing up into a number part and a variable part. When it comes to the number 108, I see that it's even, so I'm going to use factor tree method to break it down into 2 times something. 108 divided by 2 makes 54. I can keep going with breaking down the 54. It's again even, so I'll pull a 2 out and divide it by 2 and get 27. I recognize 27 as being a perfect cube. Why is it a perfect cube? Because it would be made up of 3 times 3 times 3. So since 3 times 3 times 3 makes 27, we could write that as 3 to the 3rd is 27. And if 3 to the 3rd is 27, it follows that the cube root of 27 will be 3. I'm going to take that 27 now, and I'm going to pull it out of the original expression, putting it on the left into a radical for perfect cubes. And I'm going to create another radical here for things which are not perfect cubes. So a couple of things that would be not perfect cubes would be these 2's. We don't have a triple, we only have 2 of them, so that's not a perfect cube. With the 3's, we had a triple. We had 3 of them. That's why that makes a perfect cube. So you can put the 2's behind. You could multiply them if you want to make 4. That just simplifies it a little. And now we've broken up the number part. 27 times 4 makes 108, but 27 is the largest perfect cube inside 108. We would now try to do this same process with the variables. X to the 9th is itself a perfect cube. How do I know it's a perfect cube? Because here's some perfect cubes of variables. X times x times x is a perfect cube. This would be x to the 3rd. Also, x times x times x times x times x times x is going to be a perfect cube. So in the first case, it was x being multiplied by itself. That's what made it a perfect cube. Here we have 2x's multiplied by 2x's multiplied by 2x's. So there's a triple there. It makes x times x to the 3rd. So now you might ask, what is the cube root of x to the 3rd? Well, since x to the 3rd is made up of x times x times x, it follows that the cube root of x to the 3rd is x. Since x to the 6th is made up of x times x to the 3rd, which is x squared to the 3rd, it follows that the cube root of x to the 6th will be x squared. So this is the cube root of x to the 6th. What we have is x to the 9th in our problem. So this is going to be a product of 3 x's times themselves times themselves. They come in a triple, so it's a perfect cube. And now we need to know what the cube root of x to the 9th is. Since x to the 9th is x to the 3rd cubed, it follows then that the cube root of x to the 9th will be x cubed. So x to the 9th is made up of x to the 3rd times x to the 3rd times x to the 3rd. And it is a perfect cube. For that reason, the entire x to the 9th will go under the left radical for perfect cubes. Y to the 5th is not a perfect cube, but it has a perfect cube inside of its factorization. I'll break him up into 5 y's, some of which come in a triple, but others do not. So 3 of the y's are part of a triple, 2 of the y's are not in the triple. So this y times y times y is y to the 3rd. Y times y makes y squared. So he is a perfect cube, whereas this guy is not. What we'll do then is we'll put 3 of the y's over here on the left, and 2 of the y's have to stay behind. We can now take the cube root of all this stuff. The cube root of 27, I had said earlier, would be 3. The cube root of x to the 9th will be x to the 3rd, and the cube root of y to the 3rd is just y. The other radical could not be simplified any farther. It'll just have to stay as it is. And that's our final answer.